This is a video from the Exam 4 review in my Calculus 1 class. Let's take a look at problem 1. Suppose we have the integral from -1 to 0 of x squared plus 5x dx. This is equal to 1/3 x cubed plus 5/2 x squared evaluated from -1 to 0. If I replace x with the upper limit of 0, I get 1/3 times 0 cubed plus 5/2 times 0 squared. If I replace x with the lower limit of 0, I get 1/3 times -1 cubed plus 5/2 times -1 squared. And notice how I'm subtracting these results. So here I get 0 minus, and then in parentheses I have -1/3 plus 5/2, which is equal to 1/3 minus 5/2. And then if I subtract these fractions, I end up with -13 divided by 6. And that's how you do problem number 1. Let's take a look at problem 2. Suppose we have the integral from 0 to 1 of 1 minus x to the 9th dx. This is x minus 1/10 x to the 10th evaluated from 0 to 1. If I replace x with the upper limit of 1, I get 1 minus 1/10 times 1 to the 10th. If I replace x with the lower limit of 0, I get 0 minus 1/10 times 0 to the 10th. And if you notice, I'm subtracting these results. So I get 1 minus 1/10, which is equal to 9/10. And that's how you do problem number 2. Let's take a look at problem 3. Suppose we have the integral from 0 to t of x to the 4th minus 8x plus 7 dx. So this is 1/5 x to the 5th minus 4x squared plus 7x, right? And I'm going to evaluate this from 0 up to t. So replacing x with t, I get 1/5 t to the 5th minus 4t squared plus 7t. If I replace x with 0, I get 0, and I'm going to subtract these quantities. And so the correct answer here is 1/5 t to the 5th minus 4t squared plus 7t. And that's how you do problem number 3. So let's take a look at problem 4. Suppose we have the integral from 0 to 1 of 1 minus x to the 9th dx. So here's how this one works. I'm going to let u equal 1 minus x. We call this the substitution rule. Du is -1 dx. If I solve for dx, I get -1 du. Now, when x is 0, u equals 1. I plug in here. So remember, I'm transforming everything including limits in terms of u. When x is 1, u is 0. And so this is the integral from 1 to 0 of u to the 9th du. But remember, there's a negative on the outside of that integral. But we can write this as the integral from 0 to 1 of u to the 9th du. So over here, this is 1/10 u to the 10th, evaluated from 0 to 1, which is equal to 1/10 minus 0. And so the correct answer here is 1/10. So do you see what happened? I replace u with 1 to get 1/10. Replace u with 0 to get 0, and I'm subtracting those results. And that's how we do problem 4. So let's take a look at problem 5. Suppose we have the integral from 0 to 1 of y times y squared plus 1 raised to the 5th dy. Now, I'm going to let u equal y squared plus 1. Du is 2y dy. So y dy is 1/2 du. So when y is 0, I claim u is 1. When y is 1, u equals 2. Okay, so I have to transform everything in terms of u's. So this is 1/2 the integral from 1 up to 2 of u to the 5th du. Okay, so this is equal to 1/2 times 1/6 u to the 6th evaluated from, and then my lower limit is 1, my upper limit is 2. If I replace u with 2, I get 2 to the 6th, which is 64. So I get 64 over 12 minus, and then replace u with 1, I get 1/12. And so this is 63 over 12. But remember, this can be written as the following. This is 3 times 21 divided by 3 times 4. 3's cancel. And the correct answer here to problem number 5 is 21 over 4. And again, that's problem number 5. So let's take a look at problem 6. Suppose we have the integral from 0 to 2 of y squared times the square root of 1 plus y to the 3rd dy. Again, this is going to be another u substitution problem. I'm going to let u equal 1 plus y cubed. Du is 3y to the 2nd dy. Now, I'm going to solve for y squared dy. And when I do, I get 1/3 du. When y is 0, u equals 1. I'm plugging in up here. And then when y equals 2, u equals 1 plus 2 to the third, which is equal to 9. And so this is 1/3 the integral from 1 up to 9 of square root of u du. Okay? So this is 1/3 times 2/3 u to the 3/2 evaluated from 1 up to 9, right? My lower limit is 1, my upper limit is 9. So I'm going to take the 2/9 and pull it out in front, and I'm going to replace u with 9 to get 9 to the 3/2. And if I replace u with 1, I get 1 to the 3/2, right? Now, the square root of 9 is 3. 3 cubed is 27. So this is 2/9 times 27 minus 1. And so the correct answer here is 52/9. And that's how we do problem number 6. If we take a look at problem 7, this is the integral of x over x squared plus 1 dx. Now, I'm going to let u equal x squared plus 1. du is 2x dx. X dx is 1/2 du. And so this is 1/2 the integral of 1 over u du, which is 1/2 natural log of the absolute value of u plus c. But one important thing to keep in mind is u equals x squared plus 1, and that's always positive. U is going to be greater than 0 no matter what I choose for x. And so we can write this as 1/2 natural log of x squared plus 1 with no absolute value bars around the x squared plus 1 plus c. And that's how you do number 7. If we take a look at number 8, on number 8 we have the integral of 1 over 1 plus x squared dx. So this is arctangent of x plus c. And that's all you would have to write. On number 9, we have the integral of cosecant squared x divided by 1 plus cotangent x dx. And so what I'm going to do is let u equal 1 plus cotangent x. du is negative cosecant squared x dx. So cosecant squared x dx is equal to negative 1 du. All right? And so from here, this is negative the integral of 1 over u du. And this is negative natural log of the absolute value of u plus c. But remember that u is 1 plus cotangent x. So this is negative natural log of the absolute value of 1 plus cotangent x plus c. And that's how you do problem number 9. If we take a look at problem 10, we have the integral of sine x times cosine of the cosine of x dx. Well, the inside function here is cosine of x, so that's a very good choice of u. I'm going to let u equal cosine of x. So your du is negative sine x dx. Solving for sine x dx, we get negative 1 du. And so this is negative the integral of cosine of u du. And so this is negative sine of u plus c. But remember, we have to put back what u is. U is cosine of x. And so this is negative sine of cosine of x plus c. And that's how we do problem number 10. If we take a look at problem number 11, we have the integral of sine of natural log of x divided by x dx. My inside function is natural log of x, so I'm going to call that u. My du is 1 over x dx. If it helps you, we can write this as sine of natural log of x, and then we're going to multiply that by 1 over x dx. So you can see my natural log of x is u, my 1 over x dx is du. And so this is the integral of sine of u du. And then this is negative cosine u plus c. The substitution rule transforms something that doesn't look nice into something that's a bit more user-friendly to integrate, in a nutshell. And so this is negative cosine of natural log of x plus c. And that's how we do problem number 11. And let's do one more for this video. On problem 12, we have the following. It's the integral of x over the square root of 1 minus x to the fourth dx. And so this is the integral of x over the square root of 1 minus x squared squared dx, right? So I'm going to let u equal x squared. Du is 2x dx. So x dx is 1/2 du. And so this is 1/2 the integral of 1 over the square root of 1 minus u squared du. And so this is 1/2 arc sine of u plus c. But remember, u is equal to x squared. So this is 1/2 arc sine of x squared plus c. And that's how we do problem number 12. And that's a good stopping point for this video. This is a video from the Exam 4 review, and we did problems 1 through 12. Okay, thank you.